All right. Well, I'm starting the recorder about 30 seconds ahead of time. So, what happened last week in terms of software, technology, that sort of thing? OpenAI. Sorry? Yep. So, they signed a deal with the Pentagon. It is not the Department of Defense anymore. It is DOW. It's the Department of War. Yes. So that is after Anthropic decided to kind of stand their ground of not disabling safety features of Claude. So now the entire federal government is not just the Pentagon, the entire federal government is planning to blacklist Anthropic. So no branch of the federal government will use Claude as a LLM. And also as a result of that, there's a mass uh, membership or subscription cancellation of ChatGPT. So it'll be kind of interesting to see how this plays out. I think from the money perspective, OpenAI probably doesn't care because most people are paying the $20 subscription per month, right? The Pentagon contract is probably in billions of dollars, tens or possibly even $100 billion. So I don't think they really care about the individual subscribers. I mean, it doesn't look good on paper, but after a while, people won't remember anymore. So, but it'll be very interesting to see. Um, and the other thing is, other countries. Okay, I'm not going to name the country. Have also not only do they quote unquote have their own AI, but they pirated the AI from yet other AI companies. And those countries definitely will not care about safety margin. Okay, so it's going to be the genie is out of the bottle. I think that's probably safe to say. But Anthropic has other plans, okay? Because I think they have the technology to help corporations to automate a lot of things. Software development is definitely one of those things on the menu. So that means, from your perspective, you have to kind of keep an eye on these things because otherwise you might find that you graduate with a computer science degree, like in 2 years or so, 3 years. You graduate with a computer science degree, and you think companies are looking for certain skill sets, except that is not the case. Okay, so because the expectation of what people or the role of a person in software development is changing rapidly. Yes. Say that one more time. Quantum computing. I think quantum computing is not going to replace general computing. In other words, you are not going to have a quantum mobile device. Okay, maybe eventually, like in 200 years or so, that would become reality. But right now, there's just no way to shrink quantum computers to this kind of size. However, quantum computing does address a lot of issues that silicon computers cannot realistically address. So it's not like certain things that are only computable by quantum computers, but they cannot be done using silicon computers. It has to do with certain problems are called intractable, which means it is unrealistic to expect silicon computers to solve those problems, but it is entirely reasonable to expect quantum computers to be able to solve those problems if they cannot be solved yet. Um, so that also means, so thank you for bringing that up. So that also means, if you want to diversify and be able to take on, quantum computing in your future, um, your math background has to be strong. Okay, yeah, because your quantum computing involve a certain branch of math that is not required from a computer science degree. It is based on linear algebra, okay, but it's not just linear algebra. So if you want to get into quantum computing, I think the best bet is really just to watch a lot of tutorials online, okay, maybe buy a book, okay, or just kind of go through, some, free resources to learn the math background of quantum computing. Um, because the number of people, the percentage of computer science graduates who are ready to take on quantum computing is really small. So if you're in that small percentage, then you have options. Okay. So thank you for bringing that up. Yeah. All right. Very good. But for today, we are going to go through a few more components, um, and we're going to start with a demultiplexer, okay? Because last week we talked about the concept of a multiplexer. Your lab is basically, talking about multiplexers, how to configure it, and how those configuration is going to change the behavior of a multiplexer. So what we'll do today, to begin with, is to talk about a demultiplexer, which I guess by now you probably expect. So is that kind of like a multiplexer but reversed, right? And the answer is yes. Okay. So a multiplexer has multiple input, one single output. So with a demultiplexer, you have one input and multiple outputs, but only one up to one of the output is going to connect to the input. So it is still a railroad switch, except you have one track coming in and multiple tracks going out. So you're basically routing the train and say, okay, you're coming in, but I can control which track out of all the tracks going out you're going to connect to. So that's the job of a demultiplexer. So the multiplexer is one of the plexers. So you go into the plexers family, and here's a demultiplexer. Okay. So the multiplexer looks kind of like a multiplexer, except it is kind of the other way around. It's the direction is opposite. So when you click on this, it is the input, and then the output. In this case, there are two outputs because this one, if you look at the configuration of the demultiplexer, it only has one select bit. So one select bit means you can only have up to two outputs. If you have two input pins or two select bits, then it has four outputs. If you have three select bits, then you have eight outputs, and so on. Okay, so the nested design that we talked about with multiplexer would also work with demultiplexer. If the only thing you have is a two output demultiplexer like this one, you can still, okay, by constructing quote unquote a tree of demultiplexers, you can still simulate the effect of a multi-select bit demultiplexer. Okay, it's just a little bit cumbersome and not convenient, but otherwise, it still works. So for the purposes of this discussion, we're going to say, let's make it have two select bits. So now we have four outputs, output 0 all the way up to output 3, because 0, 1, 2, 3 correspond to 0, 0, 0, 1, 1, 0, and 1, 1 in binary. So those would be what you need to present to the select bits. The select bit port would still be the one under the gray dot. So this is our uh, the select port. Okay, so it's 2-bit wide in this case. And then we also have an extra port over here because we are allowing the enable pin here. So whether we have the extra pin here depends on whether include enable is a yes versus a no. If it is a no, then it is always enabled, and that's why we don't see a pin here. You cannot turn it off. If we do have an enable pin, then you can turn it off if you want to. Just like with a multiplexer, when you quote unquote turn off a demultiplexer, you can control what does it mean when it is turned off. Okay, so now there are two settings that seem to be related, but they're not exactly the same thing. one is three state, and then the other one is called disabled output. So these two are kind of related because three state, also known as tri-state, is essentially saying it can be a zero, can be a one, or it can be a floating, okay, or don't care. But that means, why do we also have floating with disabled output? Okay, so I'm going to give you a demonstration of what that means. But before we do anything else, we're going to specify three data bits. Okay, so that means, the input pin over here is 3-bit wide now, and each one of the output is also 3-bit wide. So the best way to kind of test this out is to kind of just give us some input pins and output pins so that we can observe, okay, what happens with these output pins and whatnot. Okay, so we just have to duplicate this one more time. All right, so I think I can still kind of move these things. Yep. Okay, so this one goes all the way down here. This one goes, and we can put it here. There we go. And this one just has to move down just a little bit. Off by a little bit. Okay. This is just to make it look nicer. That's all. So right now, all the output pins are reporting, I don't know what the wire has, okay? Because basically they're all floating at this point. There we go. And then we connect the input pin to the input of the demultiplexer, and then just give it some random, quote unquote, random value. Let's just say 110. Okay. And then we need two more input pins, one for the enable, and then one more for the select bits. And because we have specified two select bits, so the input pin to control the select bits also need to be 2-bit wide, like so. All right, so now we are ready to do the experiment. But this is already telling you something about the demultiplexer as it is configured. So right now the demultiplexer is disabled because the enable pin is here, and we are connecting a zero to explicitly say that the demultiplexer is turned off. The behavior of a demultiplexer that is turned off is determined by the attribute that we were talking about earlier. So let me reselect the demultiplexer so I can actually point to the attribute. So the attribute that is only applicable when a demultiplexer is disabled output. So right now, the specification is floating, which means none of the output of the demultiplexer is specifying zeros or ones. It is essentially as if they are not connected at all. So if the output is acting as if they're not connected, then it is almost as if these wires are connected to nothing. Okay? So that's why they're called floating. In actual electronics, in circuit board design, floating is not exactly XXX. Floating means the actual observed voltage is going to depend on what is induced. Okay, if you have taken physics classes and you understand what is induction, great. Okay, but if you have not, okay, I'll just say it like, well, it depends on whether the circuit board is near the microwave and somebody is turning it on. Okay, because microwaves, no matter how shielded they are, they still emit a lot of electromagnetic wave, okay, which is going to induce current, okay, and also electrical potential onto a wire. Okay, so that means these things can just randomly register zeros and ones. Okay, but they're not very definite, they're just noisy. Okay, that's the other way to look at this. So now we can go like, okay, what is my other choice? Your other choice is a zero, which basically means, oh, if the demultiplexer is disabled, the outputs will all be zeros, definite zeros. Okay, so that means that is good in some cases and not so good in some other cases. Because right now, whether your circuit board is placed next to a microwave does not affect these output pins anymore, because the demultiplexer itself is saying, oh, these outputs are going to be zeros. Now, is the board still susceptible to EMF, coming from the microwave? The answer is yes. Okay, but the induced current by comparison is insignificant in this case, because these wires or these lines are called, we call this being driven. Okay, they're driven to a low state, as as opposed to not being driven at all when we selected the floating thing. Okay, so now the next question is, if this is controlling whether it's floating or zero, why do we have the other setting, which is three state or not? So right now, you can say, you can change this one, and nothing is changing for the output. So this three state has to do with the behavior of the demultiplexer when it is enabled. Right now, the demultiplexer is disabled, so nothing about the three state attribute is going to affect the behavior at this point because it is disabled. Tri-state or three-state only affects, okay, the demultiplexer when it is enabled. So that means, okay, so in order to test that, we're going to have to enable it. Okay, so before we enable, let's just say that we want to select 1, 0 as my output, okay? And now we can go ahead and enable it. Okay, there you go. So the demultiplexer is now enabled, which means it will connect the input to one and only one of its outputs. And which output is now dictated by the select bit. The select bit is always, or select bits in this case, is always connected to the connection point or the port that is right under the gray dot. So we are observing the input being 110 is quote unquote routed to output 2, so output 2 is also 110. What about the other outputs that are not selected, right? So now the three state um, attribute controls the unselected outputs because we basically said no to three state, so they're all zeros. So if you want to see the three state being enabled or being active, then you have to go back to the demultiplexer, go to three state, and then say yes. So now all the unselected output of the enabled demultiplexer are not being driven to either 1 or 0, and that's why they show as XXX as an output pin. So that's pretty much everything that you need to know about the demultiplexer. Okay, I see that many of you are not taking notes. I'm not going to force you to take notes, okay? But instead, I will show you where to find that information. So there are certain cases where you really do not have to take notes because the information is easily found using the online help of Logisim itself. So in this case, you go to the library reference, you go to plexers, and it is arranged exactly the same as the, this tool selection thing. So you just go to demultiplexer, and the everything that I explained is already here as well. Okay, so you will be needing this for your lab. Okay, so just remember how to get to here. Are we okay so far? Okay, so essentially, a demultiplexer is the reverse of a multiplexer. A multiplexer has multiple inputs. It will connect only one and only up to one input to the only output of a multiplexer. A demultiplexer, on the other hand, has one input only and multiple outputs, but it will connect the input to up to one of its output, and the rest would either be zeros or they will be floating. All right. Do we have any questions about the behavior or what a demultiplexer is? No questions? Okay. All right. Well, okay. So since you guys do not have any questions, and I have no idea whether that is really the case or not, okay, I'm just going to say this, okay? Being able to tell yourself, okay, whether you have some questions or not, whether you're fully understanding the material is really important, okay? I would say if I have one superpower, it is the fact that I can tell whether I'm understanding a concept or not. In other words, I know when I'm being thick and stupid and ignorant. And that itself is a superpower. Because if you think about the alternative, what is the alternative? It's me not understanding something and not knowing about it. That is much worse. Okay. So that is important. Okay. So does everybody know when you do not actually understand something? Now you don't have to raise your hand. Okay. If you say, I think I can figure this out on my own later on, that's all cool. Okay. Not a problem. But knowing whether you actually understand the concept or not is actually really important. Now, whether you get it resolved during the class by asking questions in the class, or you just jot down some notes, okay? Note to self, okay? Need to figure this out, okay? You could do one or the other, okay? Um, but being able to differentiate whether you're actually understanding the concept or not understanding the concept, that is super important, okay? It will be even more important after you transfer to a 4-year university. All right, so let me ask you one more time. Do we have any questions about the concept of a demultiplexer? Yes. Say again. What do you use it for? So you use a demultiplexer every time you have a source that is providing some kind of data. But depending on what the processor needs to do, it can go to different destinations. So essentially, it is a quote unquote a router. And same thing with a multiplexer, it is also a router. It's just that in the case of a physical switch on with railroads, the same switch is bidirectional. But in electronics, it's not worth the extra electronics to make a switch to become bidirectional. Can we do it? Yes, but it's not worth the extra silicon. So that's why we have multiple input, single output. That is what we call a demultiplexer. We also, no, the other way. Multiple input, one output is a multiplexer. Single input, multiple output, which is what we just saw, is a demultiplexer. Okay, so that's a good question. Yep. So if the enable pin is not specified or we do not have that pin, okay, so that means the you're taking out the include enable like so. No. Oh, to the input pin, to the enable pin. That is a good question. So the first thing I would do is to read the documentation if and see if it says anything about it. Okay. So we are talking about the enable pin. Okay, when zero, all output consists of all floating bits regardless of the data and select input. So it doesn't specify anything about what if it is not connected. So the only way to test it out is really to disconnect it. Or you can also make the input pin 3 state and then choose floating because that would be the same thing as not connecting it. So in this case, I cannot connect it. And you can see that by default, it thinks it is connected to a 1. So, I think this is a software thing because it is a simulation, right? So in the simulation, you can say, okay, if nothing specifies otherwise, I'm going to assume that it is enabled. But whether an actual chip would behave the same way, I cannot tell. So that's a good question. Any other questions about the multiplexer? Okay, all right. So there are three devices that will be in your lab today. This is one. So we're going to talk about the other ones. Okay, we're going to add a different circuit and we'll call this RAM. Okay, so RAM is another component that we'll be analyzing today. And then there'll be another one called ROM. So we'll start with ROM because ROM is a simpler device to understand. A ROM is also known as read-only memory, and therefore it is RO, okay, read-only. So ROM, RAM, they all belong to memory. And over here, you can see we have ROM over here. So now, the first thing is to take a look at all the attributes of a ROM component. It has address bit width, it has data bit width, and it has content. Okay, so we'll worry about content later on. Okay, um, we'll take a look at the all the ports as well. Okay, there are three ports. So the first port, the one that is on the left hand side, has a letter A on it. So this is the address port. Okay, the address port is allowing you to select any one of the bytes or the words or the locations inside the ROM. So you can imagine a ROM to be a multi-page binder, okay, where each page of the binder is a single location. It is capable of presenting the content of one of the many pages to its output. The output is the D port, which stands for data. So here's data, okay, and value loaded from address, okay? So the address is essentially a page number. You tell the ROM which page you want it to present to the output D port. So the A port is a page number. The D port reflects the content on the page that you specify. Then what about the select? Well, the select is basically controlling whether the ROM device should be enabled or not. So when the select pin, now this is really a bad name, okay, because we just talked about the select bits of a multiplexer and the demultiplexer. This select is actually more of the nature of enable, okay. So when you look at a ROM, the select port is actually more like enable. The reason why it is quote unquote called select is because that is not its full name. The full name of quote unquote the select port here is chip select. It's whether this particular chip, a ROM, is supposed to be active or not. So chip select is enabled. Are we good so far? So do not confuse, the select port as the same as the port that we also call the select port with a multiplexer or a demultiplexer. This one is more like an enable pin. If it is a 0, then it is as if the chip is not here. The output is going to be floating. And in this case, you don't get to control, whether the output is all zeros or floating. When a ROM is not selected, or when the select port is a 0, the output is going to be floating. Are we good so far? Okay. All right. So now we focus on what is the address bit width, what does it do, and what about the data bit width? So the address bit width controls how many bits do we specify, do we use to specify a page number. So when you specify address bit width to be something other than 8, okay, so we're going to choose something that is much more manageable. So we're going to change this to, let's say, a 6. So that means each page, okay, has a page number that is 6-bit wide. So how many pages can I have in order for each page to be quote unquote addressable using the A port? And you can answer with in decimal. Hmm? So what is with one address bit, I have two addressable pages because it can be page 0 or 1. If I have two address bits, I have four addressable pages. It'll be 00, 01, 10, and 11. So using that methodology, how many pages are addressable if each page is a six-digit binary number? 64, there we go. Okay, we know it is 64 because they go from 0 to 63. Because 63 is the largest unsigned integer that you can represent using 6 bits. Now, how do we know that? Because that's how VU, okay, the function VU should be telling you. Okay, we have already talked about signed versus unsigned representation. So if you are now making that connection on your own without me saying that, and you go like, oh, okay, I can just use VU or what I have learned about unsigned number representation to figure out the total number of addressable locations from the bit width of the A port. Congratulations, because you are making those conceptual connections in your head, which also means you must have studied quite a bit already, because otherwise, the concept of unsigned representation would not be floating around waiting to be connected to something else. So that is the reason why studying, quote unquote, studying and understanding all the previous concepts to be so important. Because unless you do that, your mind cannot make those connections. Okay, whether it's the professor telling you or whether you are the one who's discovering the connection, if those concepts are not just kind of floating around in your mind already, you cannot possibly make those connections. And it is about all those connections that is important. All right. So if that is the address bit width, what about the data bit width? Well, the data bit width is actually simpler to understand because all it specifies how many zeros and ones can I fit on one page. Okay, so in this case, I'm specifying to fit exactly 11 zeros or ones on each location or on each page. So we have this content here, which is now you guys look at this and go like, okay, looks like it only has 8 locations. Well, it's only showing 8 locations. To actually understand what each location has and to change those, you right click on the chip, you go to edit content, and it will pop up an edit window that looks like this. Okay. And I cannot change the font size of this thing, so I can't really make it any bigger. Okay. But in this case, if you count the number of the bundles of three bits, there should be 64 of those. Well, you can also kind of systematically, kind of count, okay? Because on each row, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So each row is representing 16 addressable locations. There are 4 rows. 16 times 4 is exactly 64. So then the next question is, ugh, then what about these little numbers on all the way to the left-hand side, and they seem to be they're slightly italic. What do they represent? Each one, okay, using my mouse pointer, each one is representing the address of the very first location on the row. So this means 20 in hexadecimal is the address of the leftmost location on this row. Okay, so if I were to pick on one, okay, like this one here, what would be the address of that location? Well, we know it would start with a 1 because this entire row is 1 something. 1 what? 1 0, 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7, 1 8, 1 9, 1 A, 1 B, 1 C. This is location 1 D. Are we doing okay so far? Okay. So remember, most things in Logisim are in hexadecimal. Okay, so when you see 20, It is not 20. It is 20 in hexadecimal. All right. Are we still doing okay so far? Maybe. Okay. So we'll go ahead and give these locations some random values. Okay. So I'll start with the one that's already selected. So we'll give it a 1, 3, F, and we'll go to this location and give it a 6 to E or 4 to E. And over here, you can just type over and specify, let's say, 2 C4. There we go. Okay. So the editor window allow you to basically hard code the content of each location, and there are 64 of these. Okay, which is if you need to hand enter everything, it really is kind of a chore. Yes. So you're talking about an actual chip, an actual ROM. So an actual ROM should give you consistent data for each location. So if it's giving you, quote unquote, giving you different values, the first thing I would check is whether chip select is enabled or not. Now, the tricky thing is in Logisim, they try to make it easy to understand. So a 1 is enabling the chip, a 0 is disabling the chip. Because most people think in that way, right? 1 or true is turning it on, 0 or false is turning it off. Most physical chips would have a slash in front of CS or chip select, which means it is active low, which means a 0 would actually enable the chip, a 1 would disable the chip. So that's the first thing I would check is whether you are actually enabling the chip or not when you specify a 0 with chip select. That should enable the chip. Hmm? Yeah, yeah. So if you look at the data sheet, if that pin is labeled with a slash, like slash CS, or with an overbar, it means it is active low, which also means a 0 is to turn it on, a 1 is to, no, a 0 is to turn it on, that is correct. A 1 is to turn it off. So I would check that first because ROMs are fairly resilient, they should not fail most of the time. Yeah, so I would check that first because most people do not understand that chip select is usually active low on the real chip. Yep. Are you trying to hack a game console or something? Question? Oh, that's a good question. Hmm. Okay, so you can actually figure that out, okay? Because we know the data bit width is 11, right? So we look at 11 bits, okay? So we go like, okay, 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, okay? So this is a bunch of 4, which means it can go from 0 to F, right? This one can also go from 0 to F. This is only 3. This one can only go from 0 to 7. Yep, there you go. Any other question? Yeah, go ahead. Okay, sure. Any other questions? Okay. So the first or the leftmost digit, which is also known as the most significant digit, can only go up to 7 because it cannot be 8 to F. Okay. But the other digits within the bunch of 3, they can go from 0 to F. All right, so now we can experiment with this particular chip, okay? So I'm going to put this one to the side over here so that we can still kind of look at these particular values. And then we will go ahead and, kind of hook up something to the address port. Yep. No, a ROM is interesting. Okay, it depends on what kind of ROM you're talking about. So, what kind of ROM do we actually have? The simplest ROM is called a just a ROM. Okay, so in the case of just a ROM, the actual content is is basically fixed from factory. You cannot change that. Okay, you basically say, I want this to be the content of all the ROM chips that I'm buying, and then at factory they will configure the inside of the ROM so that that content is basically etched in. Okay, so after ROM we have PROM, PROM. The P stands for programmable. Okay, it's called programmable ROM, which sounds to be uh, a contradiction, right? Or paradoxical or ironic. Okay. So a PROM is a device that you can purchase with no content on it. And then you have to purchase a special programmer, a ROM programmer, in order to actually specify the content. But you can only do that once. Okay. So with a programmable ROM, you can change or specify the content exactly once. After that, you can't change that anymore. If that is not what you want, you have to unplug the ROM and toss it away. Okay, so that's a PROM. So after PROM, we have EEPROM. So what does the E represent in the EEPROM? It's erasable. Okay, so it is erasable, programmable, read-only memory. Okay, that's EEPROM. So EEPROMs are kind of funky. They're kind of you can recognize the EEPROM pretty quickly because it is the only kind of chip that has a window. It has a transparent, usually it is circle, but sometimes you can see square ones, okay? So it has a window, and typically there's a taping over the window. So the way you erase it is you expose the window to UV light. Even the sun can do it, but if you expose, a EEPROM to the sun, it's going to take you hours in order to reliably erase the content, at which point you can put it back into the programmer and then reprogram the content. So that's called an EEPROM. When I started, to work in the embedded system industry, we were working with EEPROMs, and I'm the guy who had to write the firmware to run on those single board computers or SBCs. And you can only do this once, right? So I would, change the software a little bit, plug in the EEPROM, program the EEPROM, plug it in, and I don't have any debugging tool. Okay, the only tool that I had to figure out whether the software is running or not is a single LED. Did the software get to this particular point to turn on the LED? That's my only debugging tool. So you can kind of imagine that if you have to write the firmware, to the point where it can start to communicate with the PC, download the code and do all kinds of stuff, that's not easy to do, okay? Because every time you make a mistake, it doesn't work, you have to unplug physically, extract the EEPROM, put it aside because you can batch erase using a UV eraser. So at the end of like using 16 of these things, then you take a little tray of 16 of these EEPROMs, go to the UV eraser, turn on the UV thing. It has a diode mechanical timer, which is really not nostalgic. And then you can hear the clicking. After 15 minutes, it'll give you a ding. It's not just a ding like a cell phone ding. It is actually a bell inside the device making that ding sound. So everything is really kind of mechanical back in those days. Then you can retrieve the 16 now erased EEPROM, use one at a time, okay? Change your software, reprogram one, plug it in, see if the LED turns on. If it still doesn't turn on, extract that, make another change to the software, program enter the EEPROM, plug it in, and see if the LED turns on. Okay, that is how we debug programs back in those days. Okay, so a lot of the approaches that you guys do now would not work in those days. Okay, essentially you spend a lot of time just reading the code instead of guessing. I bet you if I change this thing over here, it will fix the problem. No, you try to be as sure as you possibly can before you actually do anything, because it is time consuming to go through just one single iteration. If you think that is bad, okay, it is nothing compared to the punch card days. I'm not going to get into the punch card stuff, okay? But this is nothing compared to the punch card days of mainframe computers. All right. So the address is 6-bit, okay? So we need to specify 6 bits to this input pin and just kind of stash it over here. The output would be 11-bit wide, okay? So we're gonna stash it over here, change this to exactly the same as 11, like so, and make this connection. And then we're gonna have a chip select, okay? So you can see that when the chip select is not connected, the device is by default saying, "Oh, I'm on," okay? But that is not the expected behavior on an actual physical chip. So just kind of keep that in mind. All right. So we're going to turn on the chip, okay? So go to the poking tool, turn it on, okay? So let's just say that I want to get to this location. I want to display 2C4 as a binary number. So what do I need to specify to the A port? So this is testing whether you know how to read the hex editor and also how to do base conversion. But since it's all base 16 and base 2, it is not terribly difficult. So the first thing is to figure out what is the location of the 2C4. Okay, 2C4 is the content of the location. What is the address of that location? It's a 3.8. Yep, you're correct. Because this is 3.0, 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.7. This is 3.8. So now we have to convert 3.8 into hexadecimal. Well, it is hexadecimal. We have to convert it into base 2. 3 is 1, 1. So we specify 1, 1. 8 is 1, 0, 0, 0, 0. So we put a 1 over here. So this is supposed to be the output of 2C4. 0, 1, 0 is 2. 1, 1, 0, 0 is the C. And then 0, 1, 0, 0 is the 4. So that is how you use a ROM. It is essentially an array. Okay, so if you think about it, okay, it is basically an array. And if you want to use an array to look at a prom, you're basically saying D equals to whatever the ROM is, square bracket, and then the A port is your index. So this is the quickest way to map the behavior of a ROM to a concept that you have already understood from CISP 360. Are we good so far? All right. Okay. So if we are comfortable with ROM, then we're going to move on to probably the most complicated component in the processor that we're going to use. So we go to project, and this time I think I put that in already. I just have to use it. It's the RAM component. So RAM is a part of of memory, and then you just select the RAM component and slap it here. Okay. So the first thing you notice is, it looks a little bit like a ROM. So by the way, why is it called RAM? RA stands for random access. Okay, it's random access memory. And also, by the way, I wasn't really done with all the different kind of proms or ROMs. So after EEPROM, there's double EEPROM, which is EEPROM. So now the question is, what is the extra E? What is the first E? Electrically or electronic. So double EEPROM is electrically erasable, programmable, read-only memory. What does that mean? Okay, so what that means is it doesn't need a tiny little window to expose to UV anymore. You put the chip on the programmer, and then you can start a erase cycle electrically. Okay, so what that usually entails is a higher voltage on one of the pins for a certain amount of time, and that would erase the content of the ROM. And then after that, you can reprogram that again. Okay, which is actually really convenient. So after EEPROM, we have flash memory. So flash memory, the only difference between a flash memory and also an EEPROM is flash memory usually does not need a higher voltage. So there's a special pattern of accessing the content of a page that will trigger the erasure of a particular quote unquote page. So flash memory cannot be erased. Usually they're not erased. You don't erase the entire thing. It is broken up into smaller pages. And then each page itself can be erased, but you have to trigger that operation by writing a certain content to certain locations in a particular sequence. And then it will start the erase cycle of that single page. So that's flash memory. And then flash memory would lead to solid state storage because that's kind of what we use these days. All right, so getting back to RAM. So we can see that, oh, it also has an A port, okay? Same thing, the A port specifies the location. It also has a D port. Well, this D port is a little bit different this time because it is both the output but also the input. The reason why it can also be the input is because RAM is read-write capable, okay? So something has to be able to specify what is the new content of the location that you have specified, right? So the D port is now bidirectional. It can be the output, can also be an input. It also has a chip select, okay? So once again, this is actually more like an enable, or if you want the full name, it is chip select, which is also, commented, when you hover over that. So what about the extra pins? This thing has got extra pins, right? So this is a clock pin, okay? So the clock pin is important because the clock pin is saying when should we update a particular location? It is only going to update on the rising edge or a falling edge. Okay, that part is configurable, but it is only going to update when you have an edge on the clock line. When you're reading, it doesn't matter, okay? But when you need to update, it only updates on the rising edge, I think by default. What about LD? So hover over the LD and you will see the explanation is load, okay? So that the terminology is a little confusing, okay? When it is a 1, something is reading the content from the RAM, okay? If it is a 0, then something says, hey, RAM, I need you to remember this at this location. So load is direction control, okay? Are we reading the content, which means it's a 1 for load, or are we overwriting the content, which means load has to be a 0? So the last one is clear, which is actually the same thing as the 0 port of a register. If this particular port is a 1, then it will asynchronously erase the entire content of the RAM. So every single location will go back to 0, 0. Okay? Asynchronously, which means it doesn't care about the clock line or anything else. As long as clear is a 1, it will just erase all the locations on that chip. But it has to be selected first. So if the chip is not selected, it ignores every single port. All right, so now we get to see about the same thing, address bit width. So once again, you can select, a particular bit width. So this time we will pick 5, okay? So if I pick 5, that means how many locations do we have on this RAM chip? 32, that is correct, because 2 to the power of 5 is 32. And those locations will range from 00 to 1F in hexadecimal. Okay, very good. And then data bit width is kind of the same thing as before. Okay, it basically says at each location, how many bits are we going to store? So let's just kind of be fancy and specify 16 this time. Okay, so with 16, there are 4 hexadecimal digits because each hexadecimal digit is representing 4 bits. So if you have 16 bits, 16 divided by 4 is only 4. So there are 4 hexadecimal digits to represent the content of each location. Just like with a ROM chip, you can also use a hex editor, okay? But this one is locked in with the ROM chip, so I have to kind of take it away, right click here, go to edit content, and now we can see a different hex editor, like so. And this time we only have 2 rows because each row still has 16 locations. So when we have 2 rows, we have 32 locations, and that's the entire capacity of this particular chip. Okay. So we're going to go through a few operations with this particular chip. So we'll go ahead and get rid of this, okay? Because the whole point of RAM is you can change the content on the fly without using a program. So we're gonna use an input pin. It needs to be 6-bit wide to connect to the A port. Okay. Oh, 5. Okay, I forgot. There we go. And then we have an output pin to connect to the D port for now. Okay, we're going to use an output pin. We're going to change this later, but we'll change it when later on. So this has to be 16-bit wide because that's how each location is configured. Okay, there we go. All of these require just 1 bit. Okay, so I have 1 bit to connect to select. So now the chip is unselected because you can see how all the outputs are floating. The clock is basically just a single bit. Same thing with load. It is just a 1 bit. It's either a 1 for reading or a 0 for writing. And then finally, clear is just 1 single bit as well. All right. So right now you look at this and go like, this is pretty boring. Every location is just 0, 0. So we're gonna change one of these. Okay. So Um, if you use the poking tool, you can actually click on one of them that is being displayed and change it directly. So you can click on, let's say this one here, and since it is dinner time, I'm going to say feed. You guys can actually figure out what kind of funky word you can spell using hexadecimal digits, and then the digit 5 looks like an S. Okay, so that's another digit, right? A 1 is either an I or an L, so you can actually use hexadecimal digits to spell out funky stuff. Okay, um, but feed is easy. Okay, because it just spells out like that. Okay, all right. And the next one can be dad. Feed dad. That will be me. Yes. Cool. All right. So now we go like, okay, I want feed. Okay. And also dead, DEAD, is also hexadecimal. Okay. So that's kind of cool. Anyway, so if I want 0 DAD to be the output, what do I need to do? Okay. The first thing is, what is the location? So according to this entire row is starting at 0, 6. So this is 0, 6, this is 0, 7. So you need to specify 0, 7 as the A port. Okay, so let's go ahead and do that. So 7 is 0, 1, 1, 1, and then the extra 0 is just this 1 single 0 here. We are reading, okay, so we need load LD to be a 1. We have to make sure we're not clearing the content, so we specify a 0 over here. And now with everything else set up, I can now select or enable the chip. And now we are seeing 0 DAD. The 0 hexadecimal digit is 0, 0, 0, 0. The D is 1, 1, 0, 1. The A is 1, 0, 1, 0. And then the last D would be 1, 1, 0, 1 again. So that's how we know, this is how we read the content of a location of RAM. Are we okay with that? Okay. So now we want to say, okay, but how do we change the content of a location? Okay. So let's go ahead and unselect the chip first. And then I also want to clear the content of the entire chip. So that's all we need to do is to go to the clear pin and just turn it to be a 1 and then turn it back to a 0. And you can see how everything is gone. And this is what it meant when I said asynchronous, because the chip does not even have to be enabled. Okay, as soon as clear becomes 1, everything is gone on that chip. Yep. Oh, I'll show you the clock. Because a write cycle is the only cycle that needs the clock to do something. A read cycle does not care about the clock, but the write cycle does. Okay. So now let's just say that we want to change location. Let's see what locations we can change. Okay. Nope. Okay, I think I might have turned out turn off that screen already. So let me go back and go to edit content. So let's say we want to change this location to DEAD, as in dead. Okay. So first thing is, what is the location? What is the address? So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be location 1, 9. Okay. So that's the easy part. Okay. The 1, 9 means we have to kind of retoggle these input pins to be 1, 0, 0, 1 for the 9, and then the extra one is going to go here. So that's going to be the right location. That's the easy part. And I'm going to stash this one over here. Okay. We also know that LD is supposed to be a 0. Okay, that's easy. We need to enable the chip when everything is done, said and done. We'll do that later. This is kind of a problem because in order to change the content, the D port should become an input. So that means I need to connect an input pin to the D port. Okay, which is not too difficult. So we go to the input pin, and this time I do want it to look nicer. So that means I need to change the direction of the port to the uh, to the left hand side. So instead of east, I'm gonna say west. There we go. And it has to match the data bit width of the RAM chip, which is 16 in this case. So we change this to 16. And now we can just go like, okay, can we connect this to the same node that we already have? The answer is yeah, not a problem, because the output pin does not put anything back to the node. So in this case, the potential danger is the D port of RAM and the input pin can both be driving the node that we are looking at right now. But because I can kind of specify the RAM chip to be in the right cycle. So D port is not going to be the output. So I can kind of make sure that there's no conflict, at least in this case. Okay, so later on we'll see how we can actually have a conflict. All right. Now since I want to spell out DEAD at that location, so now I have to specify D as 1101. Okay, so D is 1101. A is, oh, E, the other one is E. E is 1110. A is 1010. And then D is 1101 again. So eventually, hopefully, you will actually have the hexadecimal conversion table memorized. It's not really hard. There are only 16 items, and there's a certain pattern to it. Okay. Most computer science people will eventually remember that entire table because it's actually quite useful. Okay, cool. All right, so I think we got everything ready. Okay, so that means now I can enable the chip select. Okay, you can see that it's addressing the location here. But how come it's not changing? It's not changing because it will only change when the clock has a rising edge. Just like with a register, if you want to update a register, or if you want to update an edge-sensitive D flip-flop, the clock line needs to have a transition from 0 to 1, a rising edge. which is the same thing here. Okay, so RAM chip will only update the content when the clock line, and the clock line is the one that has a little TP or inverted V, symbol. When that line goes from 0 to 1, that is the rising edge that is needed in order to initiate the write cycle, which is what I'll do now. There you go. We just spelled out dead using binary numbers. We okay? All right, cool. So now I want to inject content to a certain location and then output that. Okay, so I'm gonna spell out doll, D-O-L-L. Okay, and the way you spell out D-O-L-L is D011. Okay, so I want that to become the output. Okay, and you guys go like, oh, that's easy. We already know how to do that. Let's go ahead and disable the chip first. Go back and specify a read cycle by changing LD to a 1. The clock line really doesn't matter in this case, but I'm going to reset it back to 0 anyway. Make sure clear is a 0 because we don't want to erase all the content. And the only thing left to do is to specify 1 4 as the address port value. This one is the one on the left-hand side of the 1 4, and then we just have to spell out the 4 in this case, which is 0 1 0 0. So now, when I enable the chip, the output should become D011, which means the output pin should read 1101, okay, for the D, 0000 for the 0, 0001 for the 1 or the first one, and then 0001 again for the last one. Okay, that's what we are expecting to happen. And of course, the way I said it is suggesting this is what in writing it is called foreshadowing, right? Which means it's not going to happen the way that we think should happen. So let's see what is actually going to happen. Okay, so now enable the chip and go like, okay, pay attention. Let's do this. It's like, what? The thing is, it's not giving you an error on every bit location. It's only giving you some errors and some non-errors. Okay, so what is going on? This is because we have a bus fight. Okay, yes, technical term. Okay, this is a technical term. This is called a bus fight. A bus fight in electronics or circuit board design is basically saying a bus itself is basically a multi-bit um, node. Okay, it's called a bus. So the this connector here going from the input pin to the A port is a bus. Okay, this particular bus has is 5-bit wide. The node that is in red is also a bus, okay? It is coming out of the D port, so you can call this the data bus or the D bus, okay? So when we say there's a bus fight, what does it mean? Well, it means, something wants to specify a 0 and something wants to specify a 1. So this input pin is actually trying to actively specify the node to be 1101, 1110, 1010, 1101, which spells DEAD in hexadecimal. At the same time, the RAM chip says I need to output D011. So that means we have 1101 as the D. That part is in common. So the two sources trying to specify the content on this particular bus are in agreement in this case. And that's why there's no problem. What about the next digit? The next digit, this one wants to spell 0, 0, 0, 0. This one wants to spell 1, 1, 1, 0. The least significant 0 are in agreement. Not a problem. But the other bits are off. They're different. Because this one wants to specify 111 over here. This one wants to specify 000 at the same location. So when one side wants a 1, the other side wants a 0, it is reported as an E, for error. So this is how you can tell there's a bus fight in simulation. So in real life, okay, if you design a circuit board that ends up with a bus fight, what is going to happen? Well, you have to think about it from the electrical or physics perspective. Okay, a zero, okay, in this case, the RAM chip wants to specify a zero at this location. The input pin wants to specify a one at exactly the same bit location. A one is a high voltage. In other words, the input pin is trying as hard as it possibly can to supply, let's see, so it's trying to sink current, okay? It's trying to sink or suck electrons, okay? That's what the input pin is trying to do. It's trying to absorb electrons. On the other hand, this one is specifying a zero, which is a negative voltage. A negative voltage is a source of electrons. So the RAM chip is trying to pump out electrons as hard as it possibly can. So most people think, well, it should not be a problem, right? This is a yin and yang kind of thing. This one is trying to supply electrons. This one is trying to absorb or sink electrons. So we should not have a problem. No, we have a problem because if there's no resistor in between, it's not controlled. Okay, so what happens when you have a large current flowing through something? How many people have taken physics? Okay, electricity kind of physics? No? Yes? Okay. So in physics, okay, when you have current, okay, I is current, which is the flow of electrons, okay, and everything has resistance to it. So when you multiply I and R, you get the voltage. When you multiply current again, you get power, okay? So this is basically power, which is energy dissipation. So you ask, what is the power dissipation in this case? What type of energy are we talking about? It is heat. So that means this configuration is going to burn out transistors. It's just a matter of who has the stronger transistor, and then the other one will die. Okay, so a bus fight ends up the components destroying themselves, which is not a good situation to be in. Then you go like, well, this is a problem, right? Because depending on whether we are reading or we are writing, we may or may not want to disconnect the input pin to this node. Okay. In other words, we need some kind of a control here. We need a clutch. Okay. Or mm, we need a way to disconnect the connection from the input pin to the D port or to the rest, basically. Okay. So let's try to figure out how to do that. We have just enough time to do this part, so I'm kind of glad that we can finish it. So let's just take this out, okay? Because I need that connection to be conditional, okay? Sometimes it's here, sometimes it's not. So there's a component that can do just that. That component can be found, I think, under wiring. It's called a buffer. Nope, it's not. Okay, so if it's not there, it is probably in base. No. Okay, where is it? It's a control buffer. It is, it's probably under gates. There we go. So it's a control buffer, and there are two. One is called a control buffer. The other one is called control inverter. We need a control buffer. Okay, this is what a control buffer looks like. It has one input on the left-hand side by default, has one output to the right-hand side by default, and it has an enable. So this is essentially really just a switch, okay? If it is enabled, which means this switch is a 1, then whatever is the input will be presented to the output. On the other hand, if it is turned off, then the input, there's no impact to the input, but the output will be floating. In other words, it is as if nothing is connected to the output. So that's exactly what we need to fix the problem that we are looking at here. So the first thing we'll do is we'll change the heading to north. Okay, so this way we can fit it right here. Okay, this is the output, this is the input, and I need to fix the data bit width here. It should be matching the D port, which is 16. Okay, there we go. So it is still having a problem because not connecting to the input or the enable is enabling. Okay, so we need to somehow figure out, so what should we connect here? Looks like LD has something to do with it, right? Because LD says, hey, if LD is a 1, don't connect the input pin to that node. If LD is a 0, then yes, we want to connect it. But you look like this and go like, but that's not going to work because LD being a 1 is going to enable the switched buffer, which means we're going to have a problem. So we need to invert the uh, polarity of LD first, and then the inverted signal will then be used to control the controlled buffer. That's not difficult to do because we have something called a NOT gate. So we have a NOT gate here. So we connect the LD pin to the NOT gate. So when we are reading, the output of the NOT gate is going to be a 0. When we are writing, the output of the NOT gate is going to be a 1, which is exactly what we need in order to control the controlled buffer. So now we have the situation, basically fixed. Because now when we are reading, the input pin, which is the square 16-bit thing, which is this thing here, is disconnected when we are reading. The output pin says, okay, great, I'm looking at the content of the location 14 in this case, which is D011. Cool, okay? But when you need to write to the content, then the switch or the control buffer will be enabled, which means the input pin will be connected to this node. And then because at that point, the D port will become an input, we don't have a problem either. So that's how we get a RAM component to work by controlling, okay? Sometimes we let other things to specify the content to the D port because D port is an input when we are writing the content of the RAM. And other times when we are reading, this will be disabled. And as a result, when we are reading, whatever you're presenting here is not connected to this node, and we don't have a conflict. So that's basically how a RAM chip is supposed to be used. Do we have any questions about the concept of a RAM chip? So once again, the built-in help also explains the RAM chip. You just go to memory library and then you go to RAM and it explains it exactly the same way that I just did. So the internal help or the built-in help of Logisim is actually quite useful. Yes. Are you talking about the control buffer? Oh, sorry. Yes. So this is the one that we do not use, okay? Because this one basically has a additional control port and it has two data port. One data port is for reading, one data port is for reading. One for reading, one for writing. Correct. But most actual RAM chips are using a single D port configuration, and that's why this one we don't really see in industry much anymore. Yeah. In fact, these are called a static RAM, which is also seldom used these days anymore because the transistor count is higher compared to dynamic RAM. So we use DRAM or dynamic RAM these days, and then we have DDR technology, which is double data rate. That's why it's called DDR. So The concept of a DDR has to do with RAM being extremely slow devices. Okay, so has anyone ever looked up, the clock rate of your RAM chips? Okay, what is the clock speed of your RAM chip? How it okay? Give me a number in megahertz, right? In hundreds of megahertz. So how fast is your RAM? Six what? 6,000? No, it cannot be that fast. That's faster than your processor. Typically, they're in hundreds of megahertz. Let's just say 300. Okay, so 300 megahertz for your RAM chip. 300 megahertz. Okay, what about your processor? What is the top clock speed of your processor? 4.6 gigahertz. Just for easy calculation, we'll say it's 3 gigahertz. Okay, so what does that mean? That means now these modern day processors, they can perform one operation per clock. So that means potentially the processor can say, I can perform 3 billion operations per second. That is pretty fast. Okay, but your RAM chipset, I can only do transactions up to 300 million per second. Yes, yes, yeah. Because of pipelining, it is possible. Yep. So now your processor goes like, okay, I'm done with this addition. I need to store the result into RAM. So it starts the operation. RAM says, oh, it will take 10 CPU clocks to perform one single transaction. So what do you think your processor is going to do in the other 9 clock cycles? It's going to do exactly this. It's going to twiddle its thumb, doing absolutely nothing because you're stuck. Okay? Double data rate is supposed to, in combination with caching, is supposed to kind of make it more efficient. Okay, so we are running out of time, so I can't really explain, why DDR technology actually helps to alleviate the bottleneck of RAM. So if you're interested, I can talk about it next time, but we are out of time today. We do have a lab today because the whole idea of explaining all of this stuff here is for your lab. So we are going to take a quick look at your lab today. It is called More Processor Components. So we'll take a look at the access key is TTP, all in lowercase, which stands for Tax Toy Processor. Okay, so all of these are leading to the processor that we're going to use in this class. So now I just have to publish this, and you should have access to it by the time you get to the lab. I'll see you all in a few minutes.